So, hi, good morning, everyone. Thanks for joining. And today we have Krishna Birla as a speaker who is a Cloudera employee, and we will talk about Apache YuniKorn. And he will cover a few topics like a deep understanding on Kubernetes resource scheduling and value Apache YuniKorn brings to it, and other few topics as well. I will ask him to share about that. Here is a quick introduction about him. He has been contributing to open source from his early college days of Google Summer of Code to his most recent contributions in Apache YuniKorn. Within his 3 years of industry experience at Cloudera, he has worked on multiple features in the domain of cloud computing, Kubernetes, and resource management for Cloudera data platform. So I will ask Krishna, please introduce yourself and then start with that. Thank you.
Thanks, Sam. Hi, everyone. So, my name is Krishna Birla, and I am a senior software engineer in Cloudera. Presently, I am in the compute platform team in the resource management project. And I joined Cloudera around 3 years ago as a part of the cloud computing team. And then I transitioned after 1.5 years into the resource management team, and that's where I've been working since. We work with a bunch of things around resource management and scheduling, including but not limited to multi-tenant cluster management, namespace management, kubeconfig, access management, and so on. And YuniKorn is an essential part of that because YuniKorn is the core logic of enforcing the quotas and enforcing the scheduling policies once they are set on the cluster.
Krishna, sorry for the interference. Will you please switch on your camera? That will help in relate and connect. If anyone else wants to switch in. Thank you.
Sure. So let me share my screen. Let's get into it right away. Before we start, let's set a very brief agenda on what we want to do today. So we'll go through some of the basics, high-level architecture of YuniKorn, what YuniKorn is, what created this use case of creating a service like this, and why the vanilla Kubernetes scheduler becomes a problem when scheduling batch workloads. Then we'll look at how to provision YuniKorn locally. We'll also look at installing YuniKorn, and that will help us get an idea of what are the different components of YuniKorn, and what are the mandatory components and what are the optional components. And then we'll go through some of the YuniKorn features that it brings over the Kubernetes scheduler. The features that we'll look at for the purpose of this talk is queues and quotas. So we'll look at how it manages multi-tenant clusters through hierarchical queue structures and how it enforces quotas in that queue. We'll also look at one of the latest features of YuniKorn, which will be shipped with the next version, which is preemption. And we'll look at how you can set preemption policies on the cluster and how it can help in a cluster which is multi-tenant, which is shared between different business logics in an organization.
Field outing.
Sorry. Okay. And in the end, we'll briefly look at user and group quotas. That is a feature which is also coming as a V next. But for the purpose of the demo, we'll look at priority preemption and queues and quotas in YuniKorn. Okay, so I'll start with the basics of Apache YuniKorn. This project was created in around mid-year of 2019 as a part of a Cloudera project, and then it was later around 2020 contributed to Apache, and very recently it became a top-level project in Apache. So YuniKorn, it's an acronym that stands for Yarn, Kubernetes, and Unified Scheduler. So as the name clearly suggests now, it's a unified resource scheduling mechanism for container orchestrated systems. And right now it has implementations for Yarn and Kubernetes because it's a universal and a platform agnostic scheduler. So it can be implemented for any container orchestrator platform. Right now implementations are present for Yarn and Kubernetes, but you can imagine that it can be implemented for any such container platforms. And it is a very lightweight universal scheduler, and the latest version which is up on Apache is 1.2.0, and the upcoming version is 1.3.0, and we'll discuss a bunch of features from the upcoming version such as priority and user quotas. And this brings a lot of things over and above the default Kubernetes scheduler. But some of the greatest, like the most important concept is the concept of applications, which helps unlock all these other features and which helps us to take a good amount of batch workloads, run it on a Kubernetes cluster in a multi-tenant environment, and something that the Kubernetes scheduler was inherently not designed for. And this concept of applications also allows us to organize jobs which make sense to humans. So for Kubernetes, every job is just a pod. But as a human who is submitting a job, it's generally a bunch of pods which are organized as an application. And that concept gets abstracted in YuniKorn. And then you can organize it in hierarchical queues. So we'll look at the queue structures, how to create them, and how to organize those in a way such that it can be scheduled, it can be sorted among itself. And this is a multi-tenant platform agnostic scheduler, as I said. So it works equally well on on-prem and cloud-based clusters. Okay, so this is a diagram which shows a bit of a high-level architecture of YuniKorn. So there are multiple components in the YuniKorn scheduler. The core of the scheduler is YuniKorn core. It's the brain of the scheduler, you can say. It is the one where all the scheduling algorithms are present, and it is the one which performs all the scheduling tasks. So for example, if there's an application that needs to be scheduled or a bunch of application that needs to be sorted based on any sorting policy, the scheduler core is where all of that is happening. And the scheduler core is agnostic of the platform underneath. So what kind of a container orchestrator system is running in the actual cluster is completely agnostic for the scheduler, which means that there has to be some mechanism to translate the container or the pod into an application. And that is where the second component comes in, which is the YuniKorn scheduler interface. So the scheduler interface acts as a protocol for converting all the way the workloads are submitted in the orchestrator system, which in case of Yarn, it would be containers. In case of Kubernetes, it's pods. And then converting those into applications, the concept of application which I talked about, which YuniKorn core understands, so that they can be then sorted, scheduled, or enforced, quota can be enforced, and so on. And once that decision is made, the scheduling decision is made, the same information is conveyed back via the YuniKorn scheduler interface. And then the YuniKorn shim layers, which are the ones running which are the ones aware of the orchestrator systems, are responsible for actually binding the pod or rejecting the pod or marking it pending or so on. So for the purposes of this particular talk, we'll mainly look at Kubernetes. So we'll be talking a lot about the YuniKorn core, the scheduler interface, and the Kubernetes shim. So for example, let's say if you submit a pod and that pod needs to be scheduled and a decision has to be made on which node the pod needs to go, the way it would be done is that YuniKorn Kubernetes shim looks at the pod. It understands the language in which the pod is written because it's aware of Kubernetes. And then it picks it up and converts that into a resource request as an application. And that goes to YuniKorn core. So YuniKorn core is really just looking at the pod or a group of pods. So YuniKorn core is only looking at a pod or a group of pods as an application, abstracted out as an application by the scheduler interface, and then scheduling it on the nodes based on the resource request. Once the decision is made on which node and what to schedule, that is conveyed back to the Kubernetes shim, YuniKorn Kubernetes shim. And then the Kubernetes shim is responsible for binding the pod to the kubelet. We'll have a look a bit for the entire scheduler cycle, and we'll look how it is implemented in the current YuniKorn version and how it was implemented originally. Okay, so this explains somewhat similar thing about the components. These are the four main components. The one component which I did not talk about was YuniKorn Web UI. So the Web UI is deployed with the scheduler in the Helm chart, and it helps nicely visualize the entire queue structure inside of the scheduler. It helps you visualize all the nodes and the applications which are running, in what queues they are running, helps you visualize easily the entire allocation of the cluster, what is the usage, and so on. We'll also have a look at the web UI as well during the demos.
Just one thing, in middle of the session, if anybody has any question, please feel free to ask.
Sure. Yeah, definitely. Let's keep it interactive. So if there's any questions, feel free to ask. So, yeah, so this is what I was.
Hi, this is Rajkumar. I joined a bit late, so I'm not sure if you already answered this, but are we going to discuss why the YuniKorn, like what current day scenarios does YuniKorn complete, which we don't have already?
Yes. Yeah. So, I'll quickly go over the agenda again, probably. Yeah, we'll discuss. We're not talking about what is YuniKorn. We'll discuss the shortcomings of the default scheduler, and then we'll how YuniKorn brings new features to those. Okay. So there are two modes of deployment for YuniKorn right now. So there's a standard mode, which is the original way of doing things. So in the old Kubernetes versions, the default scheduler of the default scheduler in Kubernetes did not expose APIs to implement or augment the individual filters and individual cycles of the entire scheduler cycle. So there was no way to augment just a part of the scheduling cycle in the default scheduler, which means that if you want to implement a different scheduler like YuniKorn, you have to replace the entire default scheduler, since there are no plugins available. And that is how originally YuniKorn was being deployed. And that replaced the entire scheduler, which means that the scheduler was replaced by the Kubernetes shim, and the entire scheduling logic, everything has to be written again in the shim in order to make sure that the scheduling happens. Whereas now, in the recent versions of Kubernetes, they have changed the scheduling architecture and introduced a plugin mode, wherein you can implement these plugin APIs which are exposed. And for every plugin API you expose, it can, so the entire scheduler cycle, as we'll have a look next, is divided into different plugins and filters, and you can implement these individual plugins and filters. And based on the error codes or success codes returned from the schedulers which have implemented the plugin, the entire scheduler cycle gets affected. And that way, without replacing the entire default scheduler, we can augment and we can change the behavior of the scheduler. And that is the plugin mode of deployment, which is what is recommended to use right now. So it's even much more lightweight, and plus it allows for pods to still get scheduled by default scheduler, choose to get not scheduled by the YuniKorn scheduler. So it brings on that functionality as well. It is completely backwards compatible with pods not looking for YuniKorn, and it allows YuniKorn to augment the behavior of the scheduler. So this is a little flow diagram of, we'll not go very deep in this, but this is a flow diagram for the plugin architecture. So this entire scheduling cycle and binding cycle creates the plugin architecture, and very recently a pre-in queue was also added. So what any scheduler plugin can do is it can implement these individual extensions, and these extensible APIs, right? They can be implemented by these plugins, wherein the plugins can return error codes or success codes. For example, in the filter and pre-filter phase, where the nodes are selected, at that point, some other plugin scheduler can implement the pre-filter and filter plugins, these APIs. And if they return error codes, or if even a single scheduler returns an error codes, even if the default scheduler allows for the scheduling, it will be rejected. And so on. And so different APIs in this scheduling cycle have different purposes. And once all of this is done, it goes into the binding cycle, where the actual pod is bound to the node. And once Kubernetes had made this plugin framework, the APIs for the plugins of the scheduling cycle available, it was very easy and made a lot of sense to implement this in a mode where it's a plugin, so that pods can choose to not get scheduled by a particular scheduler in the cluster. Okay. So before we jump into the features of YuniKorn cluster, and before we YuniKorn scheduler, and before we look at some of the demos. Let's go through some of the shortcomings of the default Kubernetes scheduler and why such a plugin is needed in the first place. So first of all, there is no queuing of workloads available in the default scheduler. So if you have a namespace and you have a resource quota defined on it, as soon as you submit the pods, if there is quota available, then that gets scheduled. But if there is no quota available, there's a straight up rejection of the pod, which means that the end user is now responsible to implement any sort of retry logic in order to resubmit the pods. Since there is no queuing of workloads, of course, that also means that if the pods are not already pending, you can also not have those pods later come up because some other pods go down. There's also no concept of hierarchical queues, which means that the entire cluster is one single queue, is one single pool of resources. What that means is if there are two applications and one is of a higher priority, it might preempt the other application, which is of a lower priority, even if they belong to different business logics. So for example, let's say if I have a cluster in my organization, which both the dev team and the prod team are using, we don't want the dev team to start up some applications, which results in preemption of applications in the prod namespaces, right? But because all of those are running on the same cluster and the default scheduler treats the entire cluster as a single static pool of resources or a static queue, that is not possible. There's no sorting of applications while preemption other than based on priority. So it does not have any awareness of what type of application is it, or it also does not have awareness of which application is long running and which is not. It simply preempts applications based on priority. We'll talk about how, in contrast, YuniKorn has a different logic of preemption and it does a lot more than just priority-based preemption. There's no such thing as gang scheduling because there is no concept of applications in the first place. Every pod is an individual workload that's running and that gets scheduled on the cluster, which means that if you write an application where you want a bunch of pods to either all be on the cluster at the same time, all get the resources, or none get the resources, that is not possible. So it might happen that a bunch of pods from a group of pods, which is an application, might get scheduled, but they cannot start execution until the other pods get scheduled as well, which means that it's a case where resources are being used on the cluster, have been booked on the cluster, but no actual workload execution is happening. As I said before, the default scheduler was never really written for batch workloads. It is very inherently a services-based scheduler. It is for stateful workloads. So it's very not ideal for batch workloads, which are relatively short-lived and which ask for a lot of resources for a small amount of time. And because, again, there is no concept of application, so the batch workloads cannot be, we cannot provide app-aware scheduling to the batch workloads. For example, if you want a bunch of pods, let's say if you are running a Spark job and there's a driver pod and a bunch of executor pods, you want all of them to be part of the same application. It's a same Spark job. That is currently not possible with the default scheduler. And as we discussed, there is cluster-wide preemption. So the preemption happens cluster-wide as it's a single queue, a single pool, and the preemption happens based on priorities which are completely user controlled. So there is no way to opt out of preemption or to specify a sort of a property which levels out the priorities given by the user. Those things are not available, which we'll discuss in contrast. That is available in YuniKorn. And we discussed the very typical issue of pods getting preempted due to preemption triggered by a completely different business logic. Okay, so what does YuniKorn bring in? So there are a bunch of YuniKorn features that are available over and above what the default scheduler provides. The first one is workload queuing. So instead of treating the entire cluster as one single queue, what YuniKorn has is the capability to define queues in a hierarchy, and that hierarchy of queues can exactly replicate a hierarchy of organization, which means that for different business logics, you can have different queues, and the queues can be configured to not interfere with each other. For example, in this particular diagram, it's a rather simplistic diagram, but still helpful to understand that there are a bunch of queues, and inside each queue, a bunch of pods have been submitted. And what YuniKorn is doing is it's taking all of the queues and the applications running inside of it, and it is sorting it based on a bunch of sorting algorithms. It can be either FIFO sorting, which is first in first out, or it can be sorting based on priorities. And similarly, it is also aware of all the nodes in the cluster, so it is taking all the nodes and sorting those as well. So for example, it can be sorting in a fair policy, which means that the nodes with the most amount of resources are first selected, or let's say it can be sorting in a bin packing mode where the nodes with the least amount of resources are first selected. And once it has sorted the nodes and the application in the queues, it can match those applications with those nodes and schedule it on that particular node, which means that in a multi-tenant cluster where there are multiple tenants, or in a cluster where the organization has defined multiple business logics, you can have applications running within those different queues representing different business logics and not interfere with each other when it comes to scheduling on a node or getting preempted from a node. Gang scheduling is what we talked about. This is a very critical feature for Spark applications where you want drivers and executors to come upon the cluster at the same time and capture all the resources at the same time. And if the resources are not available for starting all the pods in the application, then you don't want any of the pods to start. And this is a critical use case for Spark applications, which is provided by YuniKorn. And of course, because of lack of application concept, it's not there in default scheduler. And application sorting, as we talked about, so you can sort the applications instead of just the pods, which means that instead of pods having priorities and pods having based on pods getting scheduled and preempted based on just their individual priorities, you can have entire applications getting scheduled and not scheduled based on their priorities. And not just priority, but you can have other different ways of scheduling, such as state-aware scheduling, where you only want one application at a time to enter the running state from an accepted state, or you can have a FIFO-based scheduling where you want the first application that was submitted to get scheduled first, and so on. The other main feature that we'll talk about today is preemption in YuniKorn. So as we saw in the earlier diagrams, we can create a route-based hierarchical queue structure in YuniKorn. And in that queue structure, we can define quotas for all the queues. And that is where that is also helpful for preemption. We'll see how. So this is a very simple example on how a possible hierarchy of queues can be defined. As you can see here, we have a root queue. The root queue is the entire... Sorry, is there a question? Okay, sorry. So the root queue is the entire cluster capacity. So YuniKorn will consolidate all the nodes available, and that is how the root capacity is, or the root available capacity is calculated, and it's just about all the sum of all the nodes which are there in the cluster. And under that root, we can start creating our hierarchy of queues. In this example, you can see there's a queue which is system, and then there's a queue which is org directly under root. The color coding here is that the ones which are in green are the leaf queues, and the ones which are in cyan are the parent queues. The difference between leaf queues and parent queues is very, very simple. One misconception could be that it's based on the actual placement of the queue in the topology, but that is not true. Even queues which have children can also be leaf queues. The concept is that the leaf queues are the ones where applications can actually be submitted, workloads can be submitted, whereas the parent queues, the applications cannot be submitted inside of the parent queues. So that's how a parent queue and a leaf queue is defined. So here you can see the 5 queues which are in green are the leaf queues, and the other ones are the parent queues. The first parent queue is org. So that is where the organization starts, and the exact organization hierarchy can be replicated through the queue hierarchy, which really makes it very easy to schedule applications and understand what's going on with the cluster and make it a truly multi-tenant deployment. And then there's a system queue which has been created, which is a leaf queue where all the cluster critical workloads can run. And here you can see that quotas have been specified on each of the queues. So there are two types of quotas that you see. The first is max, and the second is guaranteed. So the max quota is the one which is specified to limit the maximum allocation of a queue. For example, you have a max quota of 100 on the org queue, and both of its children have a max quota of 80 and 60 respectively, which is engineering and sales. What that means is that you can book a maximum of 100 in the org at any given point of time, but that division of 100 can be divided between the engineering and sales queue such that at any point of time at max they can acquire 80 units of quota from the org. So for example, if I have the max for org as 100, and if I have applications running in engineering which want to take up a capacity of 80, then in the sales, even though the max capacity is 60, I'll only be able to provision 20 because 80 is being used by max, right? And as soon as max releases some of the resources, let's say it goes from 80 to 60, then the use capacity of sales queue can go up from 20 to 40, so that the sum is always 100, which is the capacity of the org. You can see you can kind of see what is the problem with this. The problem is that if a particular child of a parent can use all of its capacity or a huge part of its capacity at any given point of time, once it starts using that capacity, there is no way to take that capacity back from that particular queue. For example, if engineering queue starts using a capacity of 80 out of 100 from org, even though the sales has a limit set at 60 for max quota, it can never go to 60 because 80 has been consumed already by engineering and only 20 is left. And there is no way for sales to force engineering to give up that capacity. It is dependent on engineering queue to kill its pods and then release the capacity. This is where preemption comes in. So apart from max quotas, we can also specify guaranteed quotas. And the guaranteed quota is what drives preemption. That is what limits preemption and drives preemption. So again, let's look at the same example where this time the guaranteed of engineering is 50 and max is 80. And similarly, guaranteed of sales is 30 and max is 60, right? Now, if we have a similar scenario where under org, there are queues in the engineering, there are applications in the engineering queue which have consumed full 80 units of quota, and then new applications start coming up in sales. The first 20 units of quota which are used in sales will not trigger any kind of preemption because we can see that there is an available 20 units of quota from org. But after that, for another because there's a guaranteed of 30 units of quota for sales, for another 10 units of quota above that 20, it will preempt it from engineering, right? So what will happen is the engineering queue will basically will have to give up quota such that it now will come at 70 and not use the entire 80, and the 10 will be given back to sales. Now again, that results in a different problem, which you can see here, which we talked about earlier, which is that we don't want different business logics to preempt each other. So in this case, we don't really want the sales team to be preempting the pods from engineering. And that brings us to the next concept of preemption, which is preemption fencing. So in preemption, so you can see the gray boxes which have been defined around certain queues or certain queue subtrees. They are fences for preemption, which prevents anything from getting preempted, from triggering preemption from within the fence. So what does that mean? It means that preemption cannot be triggered from within a fence, but it can be triggered inside a fence from the outside world. So here in this case, if there's a fence around engineering and a fence around sales, if you have new applications starting up in sales and the guaranteed quota has not been achieved and yet the max quota is not available, those will not preempt anything from engineering because there's a fence around sales. So that is the concept of preemption fencing. We'll see all of this in the demo as well. But yeah, just going through some of these concepts so that the later slides make more sense. Coming one.
Hey, Krishna.
Hey.
Just one question. What is the unit of this, single unit when you say 100 units? So is it like 100 pods or?
Yeah, so exactly. So it can be anything. So YuniKorn allows you to specify quotas in a lot of different ways. You can specify max number of applications, which will limit the number of applications. You can specify CPUs and memory, which will limit CPU and memory. So you can think of max quota as not a single value, but rather a map, which is a map of type of resource to the actual resource quantity. But for simplicity of creating this diagram, I have just used simple numbers so that the math is easy. But yeah, you're correct. So the max is not actually a single number, but it's a map of resources. So you can think of max as specifying CPU of 500 millicores, GPU 1, or memory 500 megabytes, and so on. Does that?
Yeah, thanks.
Okay.
Hi, so query on fencing. Now, with the fencing mechanism in the last example that you mentioned, let's say if engineering has already taken 80 resources or units of resources and sales is expecting 30 when it doesn't have, and then since because of the fencing, there is no guarantee that, in fact, it's not possible to preempt the resources from engineering. It means that the guarantee value that has been set won't be satisfied to the sales queue. Is that right?
Yes, correct. And this is where the last point comes in, which is that the preemption policies that are set, they are not guarantees, but they are strong suggestions. What it means is that a best effort is made to satisfy all the preemption policies which have been set, such as the guaranteed quota or opting out of preemption and so on. But these are strong suggestions and not guarantees. And this is very important. This flexibility is very important in the cluster because these policies are being set by the end user, right? So the end user can set any sort of policy. It can configure the cluster to have any sort of policy. And so policy set by a certain business logic or a certain part of the queue in the cluster, they are strong suggestions to the scheduler, but they're not something that will bring the scheduler to a bad state. So this flexibility is actually very helpful in this case.
Got it. Just a supplement question. Without the fencing, in the same example, sales queue would definitely preempt the resources from the engineering to get the additional 10 resources, right? 10 units of resources. In that case, what is the the mechanism or the phenomenon in which the resource would get released? Does it mean that the current pods would simply get deleted, or the deployments will be set to replica 0? How is it? And what is the order in which those things happen? Will that be FIFO or LIFO?
Yeah, so all of those things are policies which can be set on the queues. So we'll take one by one. So first is yes. So the pods will be purged in. So in this case, if there was no fencing around sales, then sales could have preempted from engineering, even though there's a fence around engineering, right? But as I mentioned, fencing is implemented one way, which means that you cannot trigger preemption from within a fence into the outside world, but the outside world and into the fence.
Sorry to interrupt. In absence of fence, let's say if there is no fencing,
so if there is no fencing, then in that case, sales will trigger preemption from engineering in that case, and then that will mean that the pods from engineering will be purged till the point where either the guaranteed of sales is met or the guarantee of engineering is hit. So again, this comes back to the different laws of preemption, which is that you cannot preempt something below its guaranteed capacity, and similarly, you cannot preempt if you are already above your guaranteed capacity. And in this case, you're talking about you're discussing about what is the policy of preemption, like what preemption happens based on what. So as we discussed in, let's say, for example, in the default scheduler, the preemption is simply based on priority, right? Which means that a higher priority pod will preempt a lower priority pod. In this case, preemption is based on much more than just priority. So YuniKorn makes sure that a higher priority pods preempt lower priority pods. But even within that, it makes sure that the pods which have started first are preempted. So like FIFO pods are preempted, and then even within that, it has app-aware preemption, which means that if there's an application where there's a Spark driver and a bunch of executors, it will not preempt the driver first. It will first go and preempt the executors, because it could be a job that has been running for, let's say, 8 to 10 hours. And by preempting the driver, it destroys the entire job and it has to run from scratch again. But by preempting just the executor, later when the capacity is available, the executors can come up and resume. So there is a lot more preemption logic than just priority-based preemption in YuniKorn.
Got it. Thank you.
Yeah. So yeah.
Hi, Krishna. Follow-up question here.
Yeah.
Say, like, you while the preemption is in place, and the guarantees are not met. So by increasing the cluster capacity, will the preemption automatically happen in this case? For example, you mentioned about the example of Spark driver and executor. Say like a couple of executors were preempted to sales org.
Okay.
Now, like, the cluster capacity is increased basically. So when the cluster capacity is increased, so will it automatically take the additional resources since we have the cluster capacity increased now?
No, because let's say that this was some sort of a public cloud cluster where auto scaling happened and new nodes got added. I think that's the question, right?
Yeah.
So in that case, the root capacity of the cluster has definitely increased. But in this particular queue structure, the capacity of engineering, which has been configured to a max of 80 and a guarantee of 50, has not changed, right? So if engineering is already at a guaranteed of 50, engineering is already using let's say 50, and the pods have been preempted from sales because the capacity is not present in the sales queue itself, then in that case, and then in that case, it will not again or rather recreate the pods from engineering, right? Because at the end of the day, the total capacity of engineering plus the total capacity of sales together is limited by the max capacity of the top level queue, which is only 100, right? So the sum of pods running in engineering and sales is only is supposed to be only 100 units of quota. So if engineering was at 80 and it went down to 70 because sales had to purge 10 from it, if new nodes are added, it will not go back to 80 because 70 plus 30 equals 100 is already being used under the org queue. Does that make sense?
Yes. And a follow-up question to that. So do we have a means of defining percentage of using CPUs and cores, or is it like you need to specify a definite numbers? For example, can I say use 70% of the CPU resources from root for org and then 30% for system? So is that possible currently?
I might need to double check on that, but no, I don't think so that is possible.
Okay, thanks.
Yeah, we can, however, give weight to resources, which will change the logic on how a node is perceived as used or filled, which means that the utilization of a node can be is simply the amount of CPUs and memory being used in the node, right? But you can change the resource weights for that, which means that if you want a node to be perceived as more utilized, if more CPU is being used, even if memory is not really being used, we can do that. But for specifying the requests and the quotas, I think you have to specify the full quotas.
Okay, thank you.
Okay, so we'll also look at one example under engineering so that later the demo makes more sense. So under engineering, so we saw that the sales could not preempt from engineering because of fence, but that is not the case between test and prod, right? So, and by the way, in this example, just for example's sake, we're talking about engineering and sales, but you cannot actually submit applications in engineering and sales because these are parent queues. So let's say you can submit application in test and prod, these are leaf queues, and you submit applications inside test. Test can use a maximum of 40 right? So you submit applications. Let's say you submit 2 pods, each asking for 20 units of quota. And both of them get scheduled because max of 40 is available. Once that happens, the pods in prod come up, and prod has a max of 60, which means that it can have applications till 60, right? So let's say you start pods in that, and there are 6 pods which are asking for 10 quota each. So because the parent has capacity of 80, the first 40 pods will easily come up, because test is using 40 and engineering has 80. So there's a limit of 40 available, which will easily come up. But for the remaining 20, it will try to preempt from test. But here you can see preemption will not happen because it is already above its guaranteed, which is 30, right? So in this case, even though prod does not have any fence and it can preempt from test, it will not preempt because it's already running at 40, which means that a guaranteed of 30 has already been reached. And so it is above its guaranteed queue, right? So even if there is no fence, fence is not the only reason why queue would preempt or not preempt, of course. So guaranteed quota, that is how guaranteed quota can drive the queue preemption. So in this case, the test will keep running, and prod will be limited at only 40 quota, or rather only 4 pods if each is asking for 10. We can imagine a different scenario where the max for both prod and test, they were let's say much less. They were let's say 40 and 40, right? In this case, and let's say the max for engineering is also 40. So because engineering has a max of 40 and both test and prod also have a max of 40, what it means is engineering can run a maximum number of applications asking for 40 units of resources, and they can either run all in test or all in prod, or some in test and some in prod, but the sum has to be 40. So now in that case, where engineering is at 40 and you have all the 40 running in test, and then new things in prod come up, it will start preempting from test. So the first pod which is asking for 10 will preempt something from test, which means it will bring test to 30 and it will bring prod to 10. Again, the second pod which is asking for 10, it will preempt something from test. So test will come down to 20 and prod will come up to 20. But after this, even though the guaranteed of 30 has not been met in prod, the guarantee of 20 has been reached in test, so the preemption stops there. And as soon as, and if for any reason the test queue decides to delete one of its pods, and only after that the guaranteed is matched. So you can see again how the guaranteed quota is a strong suggestion for YuniKorn, but in scenarios where it simply cannot be matched, it is not a actual guarantee of that, because you can specify guaranteed resources of any amount in the queues. It can be something which does not even reflect the actual resources in the root, in the entire cluster as well, right? Because these are just limits. These are not actual these are not actual utilizations of the cluster. These are limits set on the queues. Okay, so we'll go through some. Before we do that, let's also have a look at some queue hierarchies. So, for example, again, this is an analog to that example which we just saw. So here you can see the root capacity of the cluster is sum of all the node capacities, and then under that you have parents, which can then have leaf queues. The leaf queues is where you submit the quotas, right? As soon as you submit something, it is a request to YuniKorn, it goes into pending. And if quota is not available, it remains in pending, in contrast to the default scheduler where it is rejected and the user has to retry. And there are different types of queues. There are auto-created queues and static queues. The static queues are the ones which you manually define, and you define it for YuniKorn. And the way that the defining is done is through a config-map, which we'll also have a look at. And then the auto-created queues are the ones which are created by YuniKorn based on configurations passed in namespaces. These can be passed via labels and annotations, for example, right? So the way you can set up queues is either through a config map where you can define the entire queue hierarchy, or through labels and annotations on namespace itself, which means that no code change is required to start using YuniKorn in your existing Kubernetes cluster. For your existing workloads, you can simply pass the configurations required for YuniKorn to pick up applications, pick up the pods by deploying YuniKorn and then setting up the namespace annotations and labels. And similarly, you can have pod annotations and labels, which will place them in the correct queues. And so the usage of YuniKorn becomes really easy for a Kubernetes cluster. You don't have to make any sort of code changes or any changes in the application context itself. The quota is set for each queues, as we just saw, and it is enforced at each level in the hierarchy, and it is enforced recursively, which is what we saw in the previous example. So in the previous example, where we saw that even though engineering and sales both have a capacity of 60 and 80 and 60 respectively, a recursive check was made with the org queue as well, which is why they were not allowed to use 80 and 60 at the same time, because the recursive check in org only allows for 100 at a particular time. So yeah, this is a similar example for how you can look at the entire tree in terms of the resources. So this also answers the other question, which is in the other example, we were just using numbers to do some easy math, but this is how a typical queue with quotas defined might look. Okay, so as I was discussing, we can set up these queues and the quotas by using a config map and using annotations on namespaces. So first is the queues which you have to set up statically. So these are queues which you have predefined, let's say something like representing the structure of your organization. And under those queues have quotas defined, and all of that can be passed into YuniKorn using a config map. And along with that, in the same config map, along with the entire queue structure, there's also something called placement rules. So placement rules is what drives the placement of workloads which are submitted, which are pods and applications, into specific queues. So there can be various different types of ways to submit a pod in a particular queue. The simplest is that you specify the queue in the label of that particular pod itself. So you can specify the name of the queue in the label of the pod that you are submitting. And YuniKorn finds that queue in the defined queue hierarchy, and it places the pod there or places the application there, right? The other way which we talked about was you can rely on auto queue creation. So let's say you have a namespace. On that namespace, you can define a parent queue, and you can also define a placement rule for creating queues based on the tags present on the namespace. This particular placement rule tells us that whenever a namespace is created, YuniKorn will create a queue for that namespace with the name of that namespace, as well as it will place that queue not directly under root, but under the parent queue, which is defined in the namespace annotations, which you can see on the right? And the quota which it will use for that particular queue created for that namespace is also defined in the namespace annotation, which you can also see on the right. What this will do is, now when you submit a pod, you don't have to specify the queue that you want to submit in. Now the placement rule is that it will automatically place it under the queue based on the namespace it was submitted in. So if you had a namespace for which a dynamic queue was created based on this placement rule, any pod that goes into that will be in that particular namespace, in that particular queue, placed in that particular queue, and it will be quota checked and quota enforced based on the quota set on that namespace, right? The other placement rule, which we'll look at in the demos as well, which is where you specify explicitly. So for the purpose of demo, we'll do that so that it's much more clear. Similarly, setting up preemption, which is the other main feature we saw, is by creating priority classes. So there is no new way of defining priority. You can use priority classes, which every Kubernetes user is very familiar with, which makes it even easier to define priorities and do preemption in the cluster using YuniKorn. So in the existing priority classes, again, you can pass annotations, which will tell you whether you want to allow preemption or not for the pods using that priority classes. This is a great thing, because it means that pods can choose priority classes and by extension choose or opt in or opt out of preemption, which means that, let's say, for example, if you have a originator pod, which results in a bunch of, let's say, executor pods, then the originator pod can opt out of preemption itself, right? So once you have this priority class created, you can go into the same config map. So it is the same config map where you define the queues, and for every queue, you also have an option to define a map of properties, right? Along with the resources and the name of the queue and all that, you have a map of properties. So these properties are what define and drive the preemption policies. So which I think there was a question on that. So for example, these are the policies which you can define for preemption. As you can see, there's a policy called preemption.policy, and the value is fence here. The other value is default, which will mean whether that particular queue has a fence around it. Then there's also a property which is called delay, which means that how much delay will be provided, or what kind of time delay will be provided before the preemption gets triggered. And then there are two different properties for priority as well. So the first is a priority fence. So we didn't discuss this. Let's discuss this. So priority fence. So once you define priority on a particular pod, right, it is defined using the priority class which the pod selects, right? But that means users can choose higher priority pods, and there is no sort of priority leveling that the admin of the organization can provide. That is where priority offset and priority policy comes in. So let's say a queue has a priority offset of plus 1000 and a queue has a priority offset of minus 1000. What that would mean is if a pod is submitted in that and it is using any priority class, whatever the priority is defined in the priority class, it will be added or subtracted, the offset will be added or subtracted to that to calculate an effective priority of the pod, which will be then used for sorting and scheduling and preemption as well. What this does is it allows for some queues to be made inherently less prior or less or more urgent in the cluster, which means that pods which are submitted inside that can kind of inherit that urgency from that queue. The major use of offset would be to use it with fence. So if you have an offset set on a queue and you also have a fence, what it does is it makes the priorities of the pods submitted inside that queue invisible to the outer world. So what does this mean? It means that it will hide the priority of all the applications which are present inside the priority fence from the outside world. So for the outside world, the priority of those applications will not be the priority class priority plus or minus the offset, but rather just the offset. This provides like a sort of a priority leveling inside of the entire queue, which means that different business logic can become inherently high priority or low priority queues with respect to one another, and still have priority and still have fine-grained priority preemption, all that happening within the queue. But between two queues with a fence, they can look at each other as inherently high or low priority queues and not interfere with each other's pods, even if the pod submitter submits a very high priority or a very low priority pod. So priority policy of fencing coupled with priority offset provides a strong functionality to do that. So once all of this is set, then you can basically start using some of those features that we discussed before. Okay, so this diagram kind of shows a good example for when the preemption can really be helpful to use the cluster resources effectively. One second. Just give me a second. Okay, so sorry. So this image shows that this is a good example of how preemption helps in mission critical batch workload scenarios. So you can see here we launched app 1, which was 20 Spark executors and 1 driver, of course. And what it does is it takes the entire capacity of the cluster, right? And eventually, as and when the drivers complete, they start dying off. The pods start dying off when the capacity is released. So if two applications are submitted at the same time, and let's say Q2 has a lower priority than Q1, then of course Q1 takes the entire capacity at the same right? But what it can't do is ask for the capacity of ask for a certain guarantee of capacity early. So now here you can see in the first diagram, if you have a queue without preemption and the queue is elastic, which means that the children can use the entire capacity of the parent, not at the same time, but individually. If that is the case and it does not have preemption, then the queue 2 or the app 2 has to keep waiting, which is in a different queue. It has to keep waiting for app 1 to release executors. And then once all the executors are released, at time T3, the execution can start in app 2. All the executors can start in app 2. Whereas if preemption was enabled, you can see that app 2 or which is in the queue 2 can specify a guaranteed capacity. So in this case, that guaranteed capacity is 40% of the entire cluster, which means that as soon as the app 2 is launched, it will preempt. It will not wait for app 1 to itself preempt the executors, but rather it will preempt the executors such that it is meeting its own guaranteed capacity. This means that more number of executors start for the Q2 and the resources of the cluster is more fair share. When we look at the preemption from demo's perspective, we'll kind of look at a scenario which will not be for Spark, but it will simulate a similar scenario for us. Okay, so here we discussed some laws of preemption, right? So we discussed that a preemption cannot happen from within a fence to the outside world. Preemption also cannot happen if something cannot preempt if it's above its guaranteed, or something cannot be preempted if it's below its guaranteed. And we also saw that preemption is something that provides strong suggestions to the scheduler, but it's not a guarantee, right? Let's simulate this scenario. But before we do that, we'll also go through provisioning a kind cluster and we'll start YuniKorn on it. The reason for doing that is so that it becomes much easier for everybody to do the same after this session. Provision. So that's why I'm making provisioning YuniKorn as well as a part of this demo. Before we go into the demo section, we'll also we'll also very briefly discuss user and group quotas. So as you saw in the previous diagrams, right, you could specify quotas for individual queues in the queue hierarchy. What you can also specify is user quotas and group quotas. So for example, let's go back to the example. So let's say I have this particular hierarchy there, and in the sales queue, I want to specify a quota of a max of 60 and guarantee of 30. We have done that. But I also want to limit how much a particular user can submit. So what this is saying is that in sales at any point of time, a max of 60 units of quota can be consumed, but it is not telling who can consume that quota. So we can specify individual quotas for individual users and groups, which will also limit the amount of quota among from the 60, which can be provisioned by individual users. So let's say I define a rule for user 1 to have only provision 20 units of quota. So that would mean that once the user 1 provisions, let's say 2 pods of 10, it will not be able to provision a third pod, even though there is capacity left in sales. And this feature is also in development, which will be released with the latest version of YuniKorn 1.30. And user and group quota enforcement is targeted for the next release, which will do exactly what we discussed. Now, the way a user is defined in YuniKorn is it's a plain string, which means that you can set quotas for that user, and when a pod is submitted, the pod can specify which user it is, right? So when I submit a pod, I can add the user info in the spec of the pod, again through annotations. So very easy configuration. And now that pod will be treated as submitted by the user is specified in the annotation. And so if that user has already reached its particular capacity in that particular queue, so it will not be allowed. You can set user and group quotas for individual queues, and you can also set it for the entire partition. So we saw in this particular queue configuration that there's a partition called default under which we define all the queues, right? So you can set individual user quotas for every cube, or you can also set it for a partition, which means basically that it's a user quota for the entire cluster. So let's say if I have a partition based user quota for user 1 of 500, then the user can only ever submit 500 units of workloads in that particular cluster. Okay, so we'll look at some of these features one by one. Let me go into my terminal. So the first thing which we'll do is we'll provision a kind cluster, right? So before we provision it, let's define an empty kubeconfig file. Let's export the kubeconfig variable to an empty file. This way, when the kind cluster is created, the kubeconfig is written to that particular file. So this is the command to create the kind cluster, right? Kind, as you might know, kind stands for Kubernetes and Docker, which is a very lightweight way to deploy Kubernetes clusters package inside of Docker containers. And it is very helpful for running things like unit tests or small demos or small or some sort of a testing for small changes and so on. It's very lightweight. It provisions very quickly, of course, and you can very quickly see because since it's a cluster running inside of Docker and in memory, you can very quickly see things happening in the cluster. So here you can see the kind cluster which I have provisioned. Let me also show you the configuration which has been used. So you can see the kind cluster has one control plane node and it has two worker nodes. Right? And all of those nodes have host ports bound to a particular container port. Right?
Krishna, sorry to interrupt. Could you increase the font size, please?
Okay. Is it fine now?
Yeah, better. Thanks.
Yeah, sorry. So as you can see, as I was saying, there's a control plane node and there are two worker nodes. And this is the kind cluster we use for all our operations. So as I said, a bunch of these features, which is the preemption and priority, which we'll look at, and also user quotas. We'll not look at a demo for that, but that feature as well is something which will be shipped with the next version of YuniKorn, which is 1.3.0, which means that I'll have to create a cluster and deploy YuniKorn inside of it by building it from the master branch from scratch. But you can easily install YuniKorn. The latest release is 1.2.0, which you can install using the package Helm chart, which is provided. It's a very clean installation, which can be easily done in any Kubernetes cluster. For the purpose of this demo, as I said, I'll use it directly from the master branch. So before we do that, let's actually also create a simple namespace before installing YuniKorn, and let's see what is the problem with Kubernetes, which we're talking about, where there is no queuing available, right? So we have created this particular namespace. In that namespace, let's create a resource quota. So this is the resource quota which I have created. As you can see, the quota is defined as a limit on CPU of 200 millicores and a limit of memory on limit on memory of 200 megabytes. If I go ahead and describe my namespace, you can see those limits are here and nothing has been used yet. Now let's create a pod inside of that namespace. So what I'll use is this particular pod. So as you can see, the pod is a simple busy box, which is asking for 200 M and 200 MI of CPU and memory respectively. This is the entire capacity of our namespace. So we should see it come up. Okay, so if I again describe the namespace, you can see that the use capacity has gone up to 200. And of course, if I do a get of pods, I should be able to see it in running status. Okay. Now we'll try to create another pod. So this time we'll create this static 2, which is asking for 100. We expect this to not schedule, but we don't expect it to get queued. We expect it to get rejected, right? So if I schedule this one, and also once it is scheduled, it's if later a capacity is available in the cluster, of course, this will again not come up. So kubectl create -f, the name of the file is static room. And you can see that it says that there's an error from the server saying that the limit of this request of CPU and request.memory has been exceeded. So the use capacity is already 200. Available capacity, which means is 0, and the requested is 100, right? Now let's install YuniKorn. So we'll install YuniKorn in plugin mode, as I had talked about it before. So the plugin mode means that the entire binding, or rather the entire scheduling and binding cycle of the default scheduler, the different steps are being implemented by YuniKorn instead of replacing the entire default schedule. We saw the diagram as well before. So let me again go to commands, and before installing, create a namespace. So we'll use the YuniKorn namespace to install all of the YuniKorn specific artifacts. Now, because this is a kind cluster, and I don't want to pull the images from the upstream, right? Because this Apache YuniKorn image is available upstream as well, but I've built it locally. So I'll load my local images in the kind cluster so that the pod which is running the master branch code. So I'll load both the web image as well and the scheduler image. So now both the images are available in the cluster. And the way my spec is defined is that I am using policy of if not present. So I expect those images to get pulled. Okay, so let's start deploying artifacts for YuniKorn. The first one is a bunch of RBAC objects. So a bunch of role bindings and cluster bindings are required for the scheduler to perform all the operations. The second one which we are doing, and of course, this is a very simple Helm install process, but since we are deploying master code built from code, master branch built from code, that's why we're having to do this. The second file which we have deployed is YuniKorn defaults. It's a config map. So let's go to that. So you can see this is the YuniKorn defaults config map. The YuniKorn default config map is also deployed with the YuniKorn Helm chart. It is managed by YuniKorn if you deploy using Helm chart. What it does is it provides a bunch of default values for a bunch of configurations of the scheduler. And these default values can be overridden by the another config map which we talked about, which is YuniKorn configs, which we'll also deploy. So the reason for deploying this is to keep it close to the way it is when you deploy with the Helm chart, so that when you deploy with the Helm chart, this does not confuse you. But that is the purpose of YuniKorn defaults, is to provide a bunch of defaults, and we don't expect users to edit the default config map to change the values of those configurations. We expect them to provide it again with as an override in the YuniKorn configs config map, which is managed by the user. So the default config map is nothing but just two configurations. The first is bypass authentication, which tells that any user can submit pods to the queues, which is what we want for now. And the second one defines the queues.yaml property, which is nothing but the entire queue structure which we talked about. So as default, we'll ask YuniKorn to only have this particular queue structure, which has one partition, the default partition. Under that, the placement rule says provided. So this is what we talked about. So the earlier placement rule, which we saw in the presentation, was different. It was telling that the placement of applications will be based on the tag of the namespace, and create true means that if the namespace, if the queue for the namespace does not exist, create it dynamically. Whereas now, for the purpose of the demo, we'll use another placement rule provided, which means that the queues will not be created dynamically. We'll create the queues ourselves using the YuniKorn config map, and we'll provide what queue to place what pod in the pod spec itself, which we'll see in the pod spec. The node sort policy is fair, which also we talked about. So the fair policy means that the nodes which have the greatest amount of available resources will be used first. This is really good for on-prem, so that the workloads are distributed fairly among all the nodes. But for something like a cloud deployment, you can use another node sort policy, which is bin packing, which is the exact opposite. What it does is it chooses the nodes with the least amount of resources first, so that new nodes are only auto-scaled and provisioned once needed, right? So the nodes which have some capacity left, we use that first so that the other nodes can go to a usage below the threshold and get destroyed. And that way you save cost on cloud. Then there's a queue structure defined. In that queue, we only have the root queue right now. And root queue is, of course, the parent queue, which means that you cannot directly submit applications in the root queue. Okay, so the next thing which we'll create is we'll create an override for this particular config map, which is the YuniKorn config map. So if you deploy YuniKorn using the Helm chart simply, you don't have to deploy any of these, but the YuniKorn config map does need to be deployed by the user because this is an override over the YuniKorn defaults config map, which means that all the queues which we talked about, all the queues and the quotas for those queues in the user quotas, the preemption policies, all of that is to be defined in the YuniKorn configs. Once it is defined in this particular config map, YuniKorn can read it. And then as soon as a pod is submitted with a label that says place it in this queue or that queue, it goes there. And similarly, if pods are submitted and preemption has to happen, it happens based on these policies, based on in which queue it is. So let's have a look at this particular file as well. As you can see, this is the entire config map. The only property which we want to override is queues.yaml. So for this property, it will pick the value from YuniKorn defaults. And for queues.yaml, it will pick the value from YuniKorn configs. I hope that makes sense. So again, in this, we have a default partition. We have a placement rule of provided, and we have a node sort policy of fair. But under that, we have a queue hierarchy pre-created, which I had created before the presentation. So what it is asking is there's a root queue. So let's remove this so that it can parse the YAML. We'll add it again. So what it is saying is there's a root queue, which is a parent queue, right? The submit ACL is basically saying that any user can submit in this queue, whereas we could say, let's say user 1, which could only allow user 1 to submit in the queue. Apart from that, the parent suggests that you cannot submit applications directly under the queue. So that's why we create more queues under it. The first queue is a system queue. The system queue is where we'll run the cluster critical applications, which we don't want to get preempted. The system queue does not have any fencing or anything around it, as we saw in the diagram. And it is a leaf queue, which means that applications can be submitted inside of it. Next, what we have is, one second. Yeah, so next what we have is under the root itself, alongside system, we have a sibling called OR. This again is a parent queue, and this again does not have any fence defined around it, as we saw in the diagram. And this has a total memory of 400 and 400 for memory and CPU. So vCore is an alias for CPU. And similarly, system has a memory and vCore of 300 each. Under OR, we have two organizations or two business units. You can see how easy and intuitive it is that the entire structure of an organization is very authentically defined inside the queue structure itself, which means that you don't have to have a mental mapping of the workloads running in your cluster and the resources they are consuming and the owners of those business logics of those workloads. So under OR, we have sales. Sales is again a parent queue, which means you cannot directly submit applications under it. And you can see that we have a property called preemption.policy, which is fence. Under sales, we also have its resources defined. You can see that it uses a memory of 200 and it has a guaranteed capacity also of 200, right? We have queues under sales as well, which is prod and test. Again, what we saw in the diagram. And this time prod and test both are leaf queues. So they have parent false because this is where we'll actually submit our applications. They both have preemption delay of 15 seconds. So the default delay is of 30 seconds, but to keep the demo fast, I've made as 15, which means that once a pod is scheduled and if all the laws of preemption are satisfied, the preemption will happen after 15 seconds. And it has resources defined, again, max and guaranteed. Memory and CPU have been defined as 200 for max and 100 for guaranteed. So alongside we have test. Now test both has a fence as well as a delay, which means that anything from prod can preempt things inside test, right? Because you can send preemption trigger inside a fence, but you cannot send preemption triggers from within a fence to the outside world, which means test will not be able to preempt from prod, which is exactly what we want. Very similar, in fact, exactly similar hierarchy has been created for org.eng. So eng, under that we have prod and we have test. Okay, so now that this YuniKorn config is created, let's go ahead and actually deploy the scheduler. So here I'm deploying the scheduler in plugin mode, which means that it will be running alongside default scheduler, or rather augment the default scheduler. You can see that it has deployed a deployment. It has also deployed a service as well, right? So this is the service which will expose the web UI. So let's actually have a look at the web UI. So you can have a look at the web UI simply by port forwarding it. So I'll do a kubectl port forward. This is where the service is running. 9889 port is where the service is running. So if I go to Google Chrome and refresh this page, so this is the entire YuniKorn UI, which you can see right now. So if I go to dashboard, you can see that there are no running applications. The node sort policy is fair. The partition being used is default and so on. If I go into queues, you can see there's only one partition, which is default. And if I go to root queue, you can see that it gives me a nice description of what is in the root queue. So it has a max memory of so and so. This has been taken directly from the consolidated capacity of the entire cluster. So that means the 3 nodes. If I expand root, you can see there's root.org and root.system. If I click on root.system, we specified a max of 300 and we did not specify guaranteed, which is exactly what we see. And similarly for org, we specified 400 and no guarantee. Under root.org, we have engineering and sales. You can see for both of them, we specified a priority fence, a preemption fence rather, and we see that here. You also see guaranteed and max under both of these queues. Let's expand any one of them. So under engineering, we see prod and test. Again, in prod, we see the name of the root, we see the capacities we have specified, and we also see that we have a delay of 15 seconds in preemption, and we also have a preemption policy as default. So there is no fencing around prod. But if I click on test, you can see that there is a fencing around test. So very similar things under root.sales as well, root.org.sales as well. So now that everything is set up, we can start actually creating some queues, or rather some applications inside these queues. So demo 2 was the namespace name where I had shown how Kubernetes fails to do all of this. The default scheduler is incapable of queuing workloads in case of quota not matched. But now let's go ahead and create the other namespace, which is demo 1. The difference between these two namespaces is very clear. So this is the demo 2 namespace, which is a simple Kubernetes namespace. And in case of demo 1, you can see that we have an annotation called YuniKorn enable YuniKorn true, which is basically telling YuniKorn to pick all the pods in this particular namespace for scheduling. So the pods in this namespace will be used for scheduling, will be scheduled via YuniKorn, right? So this is the demo 1 namespace where we'll submit all of our pods. Okay, so again, going back to the list of commands, the first one is where we'll deploy a bunch of pods inside the system queue. So by the way, let's look at the pods as well. So you can see the pods, all the pods look exactly same, system 1, 2, 3, and 4. All of them are asking for 100 and 100, 100 M and 100 M of CPU memory. These are simple sleep pods. They specify a scheduler name as YuniKorn, which means that they are asking to be scheduled by YuniKorn. They specify an application ID and a queue name as well, because if you remember, the placement rule said that we will provide the name of the queue instead of it getting automatically picked from tags. So the pod itself are providing the name of the queue they want to be scheduled in. So this pod will go into root.system. Similarly, I have system 2, system 3, and system 4. So let's go ahead and create these pods. So this should create all the pods with a delay of 2 seconds. The reason for giving a delay of 2 seconds is to clearly show also the FIFO-based preemption as well. So when a preemption needs to happen, and there are a bunch of candidates for preemption, we'll see how the preemption policy is decided based on the pod which is longest running and the shortest running.
Hey, Krishna, a quick question in the pod definition file. Since the namespace was created with the YuniKorn scheduler, is it mandatory to put the attribute of scheduler in the pod definition as well?
So I showed that for for purpose of the demo, but here we are running only the scheduler and we are not running any admission controller. Okay, so we'll discuss this actually later. I have it planned. We'll discuss what the admission controller is. It is also another component of YuniKorn, which is not mandatory. But when you deploy using the Helm chart, which is Upstream Helm chart, you also get an admission controller from YuniKorn. The job of the admission controller is to make it even more easy, even further easier for the user to use YuniKorn. So instead of you having to specify these labels and annotations everywhere inside the pod, right? Inside the pod you submit, you can have an admission controller. The admission controller will intercept all the pod requests and it will do those labeling for you. And you can have properties in the admission controller to tell how it wants to do that labeling, right? So in this case, I'm not using any admission controller, which is why I'm specifying everything from application ID to the name of the scheduler to and also the name of the queue where I want to place it. But ideally, YuniKorn can do all this for you. So it can place it in a queue automatically. It can also, based on, of course, the name of the namespace which you're deploying it to, it can also generate application IDs for you if you want. So yeah, all that is
to clarify, if the namespace is created with the annotation or label of YuniKorn scheduler, we simply can schedule a pod without specifying the actual scheduler, right?
Yep. And when you do a get on that pod, you will be able to see these labels, even though you did not put it there. So that is because the admission controller is working in the background.
Understood. Yeah, thanks.
So I go to the pods and you can see 3 pods are running and the 1 pod is pending, which means because if you remember that the capacity of root.system was 300, right? So YuniKorn has started 3 of the pods, which asked for 100. And you can see that it has beautifully put the 4th one in pending, which means that if one of those pods are deleted, the 4th one will automatically come up and start running. So let's do that. In contrast, you saw that in default scheduler, it got rejected outright. So if I go ahead and delete the pod from demo1 namespace. So the system 3 pod has been deleted. Now, if I do a get of all the pods, ideally the system 4 pod should be in running state because the quota has been made available. Just give it a second there. Okay, so if I do a get of pods, yep, so it has started the container. The kind cluster is running a bit slow, I think, because of some resource crunch on the laptop. It's of course a local Kubernetes cluster running inside Docker. But yeah, so as you can see, the pods are up. Now we'll very similarly create other pods. So now there are 3 pods in the system namespace. We'll very similarly create pods for test inside the sales, right? So I create pod inside test. So it will create 2 test pods. And similarly, I'll create pods inside the engineering test as well, right? So you can see these pods have started. And right now they have capacity. So all the pods are in running state, right? All the pods are running. Now let's say I have new pods in prod, correct? So I create pods in sales or sales prod. So now if we wait for, let's say we do a sleep of 15 seconds. Let's do a watch on this. So what we expect here is that none of the system pods should get preempted. So as you can see, right, as soon as 15 seconds elapsed, the sales 2 got preempted, sales test 2, because we had configured a capacity in sales.test as 100 guaranteed, even though the max was 200. So it started with 200 because there was no one else claiming. But as soon as prod claimed, and there is no fence around prod, So say it kicked out things from sales, right? Sales.test. But you can see that it did not kick out something from engineering.test, right? Because there is rather a entire fence around sales itself. So this means that sales will not kick out anything from engineering and vice versa. But sales.prod was able to kick out pods from test. And if you also look, have a look at the pods which were kicked out, you can see that, and also you can see that the single pod is still pending because only one pod was kicked out because the guaranteed was 100. So it cannot kick out above guaranteed of test. And you can see that sales test 2 was preempted, right? The reason sales test 2 was preempted because it was created later. So it's the pod which is longest running is not preempted because the longest running job has done the most amount of work, right? So it's first in, first out. So it's rather last in, first out, which means that the pod which is the shortest running, it gets preempted, which is why sales.test2 got preempted. Similarly, if I create apps inside of engineering.prod, right, it should also preempt, but not from sales.test, but only from engineering.test. So let's have a look at that as well. So right now you can see that engineering.prod is both in pending, right? But eventually it should preempt something from engineering.test and it should preempt test 2, which has happened. And now eventually one of these pods will be ready for scheduling and it will be created. So you can see prod 1 was created because it was submitted earlier. So you can see how while preemption, last in, first out was used, and for scheduling, first in, first out was used. So these are the different policies which you can very easily specify on the queues. So you can see how this is, even though simple, but a very strong framework for managing your quotas in a cluster, for managing quotas in a hierarchical queue structure, which is exactly how a multi-tenant organization looks like, where there are multiple tenants which don't want to interfere with each other, or multiple business logics which don't want to interfere with each other. So that is what I had for the demo. I think we can go to the end of the meetup. We can have some questions, Sam. Before we jump into questions, I have a little request from all of you. So I expect that this was helpful and that you understood what are the shortcomings of the default scheduler in Kubernetes and how YuniKorn provides serious enhancements to it. What I would expect is for all of you probably to explore more how scheduling works in Kubernetes and how YuniKorn enhances it. And at least half or more to install YuniKorn on an actual Kubernetes cluster or a kind cluster and play around with its features, which is why I plan to also show the provisioning of the cluster as well and installation as well. And probably half of that or more to deploy it in test intent stage environments for internal business logics. And then if we have at least some people deploying it in production environments, that would be really amazing. It can unlock a lot of features for your production environment. It is already shipped as a part of the Cloudera platform, for example, in Cloudera. And then, of course, this is an open source project, so it would be nice for if we get a bunch of contributors from this talk, which can contribute back to the community. Sam, can we open the floor for questions?
Yeah, sure. Thank you so much, Krishna. You have nicely covered like all the topics which were required for a basic understanding first, and how we can download it, how we can become a contributor and a committer. You have shown the demos as well to go, and which will help people to understand how to go about it. So I would request if anybody has any questions, so please unmute and ask. Rajkumar, you are not audible. Please be little.
You're not eligibly audible. Can you speak up?
Oh, sorry. Is it better now?
Yep.
Okay. Let me repeat. So during the installation, you discussed about a file that was the RBAC file, if I remember, that was required for the cluster binding. is that a default file that we get from the Apache YuniKorn website, or do we have to configure it somehow so that it works with our environment?
No. So of course, as I said, right, for the purpose of this demo, I wanted to show some features which are coming in the next version of YuniKorn, which is why I had to go through all the fiasco of building the master branch and deploying the components one by one. This is a very nicely packaged Helm chart. YuniKorn is available as a nicely packaged Helm chart. The user doesn't really have to do anything. There's just one install command, which is Helm install YuniKorn, which will pull YuniKorn from the upstream Helm repositories and install it for you. So that installation will include everything. It will include YuniKorn defaults ConfigMap. It will include the scheduler and the admission controller, as well as the web UI. It will also include all the RBAC files and the controllers required for running YuniKorn in the cluster. So you don't have to do any of that.
Okay. Then have another question. I come from a support background. So let's say this is regarding the preemption things that we have discussed. Let's say due to some new applications coming in, we have terminated other running applications. Is there a persistent logging of these events that is happening in YuniKorn?
Yes. So for example, let's I hope I'm still sharing. Yes. So we can actually go and look at some logs. That would make sense probably now. So if you see there's only one YuniKorn pod running, when you deploy using the Helm chart, you will also see another pod, the admission controller, but right now it's only one pod. And if I do a logs, so you can see, right, all the applications which we had submitted, you can see exact logs for how they were sorted, how they were pre-filtered. So you can see it went through the pre-filter phase, the filter phase. These are the phases of the scheduling cycle we discussed. And then it finally bound the pod. You can see the namespace, the pod where it bounded, the task ID, the app ID, the node which was assigned. So yeah, it's all the everything is available in the YuniKorn logs, of course. Yeah.
Okay.
Yeah.
Thank you.
Hi, Krishna. This is Karthik here. Thanks for the session. I have a really quick question. Thanks for clarifying that we'll be installing this through a Helm chart. What does it mean to an end user? For example, let's say they're using a CD workload or maybe perhaps a machine learning workload, right? So typically in a public cloud or a private cloud cluster in CDP, all they have to do is create those workspaces or set quotas in the user interface. Is that going to be the same? Is YuniKorn going to be CDP aware?
Yeah. So in fact, it would probably not be right to call YuniKorn CDP aware, because it is really agnostic of what is running on the platform or what the platform itself is, right? So ideally, it would not matter. Of course, it works very seamlessly with CDP applications, but it would not really matter, because the way you would submit your applications to namespaces will not change. All you have to change is all you have to change in the cluster is install YuniKorn, define the queues, and then once the queues are defined, those queues are attached to namespaces, right? So once you submit pods in those namespaces, which are your workloads, your CML sessions or your CD virtual clusters or whatever it is, then in that case, those are automatically placed in the queues for you, and they're automatically bound by quotas. This is, you can imagine this is particularly helpful in a case where clusters are shared between different tenants or different experiences, in which case that sharing is inherently hierarchical, and YuniKorn queue structure is of course also hierarchical. So you can do a one-to-one mapping of those tenants or those particular experiences to the queues. And even if the cluster is not shared, we saw how preemption can be helpful. So if you have multiple workloads deployed, or if you have some jobs which have been running for, let's say, 10 hours, and some high priority job comes out of nowhere and kills it. So those things can be preempted using YuniKorn as well, because the preemption is not just priority based, it's also app aware, it's aware of how long it has been running and so on. So yeah, for the end user, the experience should not change at all. The integration is seamless. In fact, there is no real integration to be done, no code change. You just have to start passing new annotation and labels into your workloads and pods.
Okay, fair enough. So you showed us a YuniKorn user interface. Does it mean that the users have to go and set the quotas and limitations in the YuniKorn interface, or that's
No.
just for our reference?
Yeah, that is a read-only interface. So let me go back to that. This is a static website. It's only for read-only. You cannot actually set things on the queues right now.
Okay.
Yeah, you can.
Everything is done in the same fashion as today, and you just need to use labels.
And you can basically look at things. So for example, you can see in the default partition in the root org sales prod queue, I have, let's say, an application running. If I click on it, you can see it's running on this particular node. So it's particularly informational. It shows the entire brain of YuniKorn, kind of presents it to you in a readable, human readable way.
Okay, cool. Thanks.
Hey, Krishna, I have a question on this users and groups. So I just saw like the queues can be restricted like for certain users. So is this the Kubernetes users, or like do you maintain like some like RBAC kind of things for YuniKorn itself?
No. So these users are not these users are not defined inside Kubernetes or any kind of a user management platform. You can create users in YuniKorn, configure users in YuniKorn, which can be any strings. So it can be Krishna, Karthik, user, and user. It can be anything, and then you can use those same usernames while submitting pods. When you come to authentication, then yes, you can have those users being restricted in terms of if they can come and pose as a user or not. But that's a different part of the story. For just enforcement of quota, all you have to do right now is set users. What is the background logic to map those users to actual service accounts or entities is left to the user. What YuniKorn will do is, once you pick an entity and there's a user attached to it, it can be service account name as well. You set that name in the queue, you set a quota for it, and then you create a mechanism such that any pod using that service account has a label with that user, and that simply will be restricted for submitting more than the specified quota of that user. So these are
Okay, so even the service accounts can be specified. Okay.
yeah, because these users are just strings for now in the way they are specified and passed in the labels, right?
Okay, got it.
Cool. Any more questions?
Yeah, I have a question regarding preemption. So as we saw in the demo, when one of the leaf queues started preempting and then one of the pods got purged, is there a possibility that we can set maybe a purge policy kind of thing where the pod, the deployment would actually be scaled down to 0? And then when the queue that needed resources and when the workload is complete, and then the pod can get back to the original replicas.
Oh, yeah. In fact, that is precisely what will happen. So as you saw in the example which I specified, right? I was creating pods directly. It was not managed through a replica set or a deployment, right? Which is why when it was purged, it basically went away forever. But ideally, what will happen is when a preemption happens and it purges a pod, it will delete it, and then the replica set kicks in and recreates it, but that recreation will leave it in pending, and as soon as the resources are available again, it will of course go to running again.
Okay.
Yeah, that is one of the key features of YuniKorn, to keep pods in pending for looking for resources.
Okay.
Can I have a question? Like, hello?
Hello. Yeah.
Yeah. So, maybe I missed it. So I was curious about like, does it replaces hardware, or like, does it work with a support high voltage, any relationship between the traditional workloads from Cloudera? Like,
So
I see Spark examples mostly. So
yeah.
how?
So the way I would put it is, Yarn on Hadoop was created for mainly batch workloads, right? So it was created for Spark
Right.
on, And similarly, Kubernetes scheduler is inherently a services-based scheduler. So it is created for running deployments on Kubernetes, long-running services which have states. And YuniKorn sits in the middle, so it can very well do the batch workloads, which come for a relatively small time and require larger resources, whereas it can also do services which require smaller resources, rather less resources, but over a longer period of time. And because it can do both, it's not augmenting, or it's not it's basically an alternate for YARN and an alternate for Kubernetes. So you can basically augment it with YARN, just like you augmented it with the default scheduler, which will give YARN capabilities to all the YuniKorn capabilities in essence. It will give capability to also schedule long-running workloads well. Whereas to Kubernetes, it will augment and give capabilities to schedule batch workloads well. So it's just dependent on what shim you write, right? Let's say you have a different scheduler, completely different scheduler, and you write a shim for it. As soon as you write a shim for it, you can deploy YuniKorn. YuniKorn core does not change. So the core logic of YuniKorn of sorting applications and queuing applications, that does not change. So you can deploy an YuniKorn in your cluster, and you can write a shim for it. As soon as you write a shim for it, it is the responsibility of the shim to take the workloads, and instead of passing it to the scheduler, whatever the scheduler was there in the cluster, pass it to YuniKorn and then do binding of the containers or the pods, whatever it is, based on whether it's YARN or Kubernetes.
Okay, so YuniKorn can run on both of YARN and Kubernetes, right?
Yep.
Okay, I see.
Yep. And any other orchestrator system that we can think of. It's a universal scheduler, agnostic of the platform.
Yeah, like, is there any existing example of Hive supported YuniKorn, or is it like work in progress thing?
So you mean support for, sorry, I missed it. Support for what?
Like, yeah, like Apache Hive is one of the like main product in Cloudera, and is there any roadmap to convert or add some support Hive on YuniKorn, or?
So there is no roadmap as such as of now. I'll probably need to confirm on that, but for now, yeah, I mean, so basically other logics, right? Like, for example, not preempting originator pods, those only exist for Spark, Ray, MPI, those things. But ideally, you should be able to schedule anything, like, let's say whether it's Hive on Tez or you should be able to schedule all of that using YuniKorn if it's in a cluster where YuniKorn is deployed. It might not be supporting the over and above logic of recognizing driver and executor pods automatically, which is does with Spark, but simple scheduling of workloads will still happen.
Thank you.
And all of the queuing features with it. I mean, the queuing, the quota enforcement, the queuing of the workloads, the concept of application where it's grouping workloads in application, all of that can still be done.
Okay, thank you.
Hi. Can you talk a little bit about the gang scheduling actually that you talked about earlier? How does that would work with preemption and then other details?
Okay, so gang scheduling is something which you can enable. It's not a so I'll probably talk a little bit about what gang scheduling is in the first place. So gang scheduling basically tells you when you want a bunch of pods in an application or a bunch of applications itself, if you want all of them to schedule at the same time, which means you want all of them to only schedule when resources for each one of them is available. Either you don't, and in other case, you don't want anything else to schedule from that particular application. In that case, you can use gang scheduling. The way to use gang scheduling right now, and there is a good amount of documentation upstream on this, which I can share later with you guys. You can connect with me. Is by defining annotations which are called task groups. So each of these gangs are called task groups, and you can define these task groups as annotations on the deployments itself, on the pods, and all the pods which have the task groups defined So if you define it on one pod of an application, it is automatically treated as the same task for the entire application if it has the same app ID. And once you define that, it will do it will basically do all the scheduling as a gang. Preemption will work differently with it. So with preemption plus gang scheduling, it does not mean that it will either preempt the entire application or nothing. It will still go and preempt the executors. But once the executors are preempted, in that case, you don't have the application will stop running because the application requires all resources to run, right? So there's Upstream documentation on this, and I can share more resources on this with you guys. How gang scheduling works with preemption.
So I wanted to talk about specifically regarding this. Let's say there is a Spark job running, which is running with one driver and then two executors. And let's say another Spark job but has to run. Now it's the same, let's say another with one driver and the two executors. Will the earlier job gets preempted? Let's say the executors get preempted. Or can we say that, hey, let the first job run and this whole Spark job actually will wait till that first one runs, and only after that this can run actually. It will be possible to explore all sort of these options, right?
Yeah, so it will depend on a bunch of policies. It depends on how the policies have been set. So the first is if the new Spark job is of lower priority, it will simply not preempt it. But if it's of higher priority, then it will start preempting the executors first till a point where the other job, if it's in a different queue, the other job will go till its particular guaranteed capacity. Either the first job will go down to its own guaranteed capacity, or the new job will come up to its guaranteed capacity and the preemption will stop. And one key thing to notice that these two jobs have to be in different queues for preemption, right? Of course, it does not make sense for two applications in the same queue to preempt each other. It's of course a cyclic deadlock. No, it will keep preempting each other, right? So applications, this is one of the laws of preemption in YuniKorn, which is that applications will only preempt something in a different queue. So if these are in the same queue, then it will simply wait for the other one to run. If it's in the different queue, it will preempt based on the policies which have been set. So if there's a fence, it will not preempt. If there's no fence, but it has a lower priority, it will not preempt. If it has a priority equal or more, but then the guaranteed is already reached, then it will not preempt. But if all of those things match, then it will preempt based on the policies we saw. First being originator pods will be preempted last, or not preempt, try to not preempt originator pods. And the second is the least running ones will be preempted first. Does that answer?
Yeah. This has been very helpful. Thanks a lot. I was wondering, is there any sort of examples, like can you include some resources where people are doing like this, combining like all of this sort of strategies? Is there any like built with YuniKorn sort of website that I can see that how people are using it?
Sure. So there is very good documentation on YuniKorn website itself. Let me show you. So there is a documentation on YuniKorn website. You can look at it from a developer's perspective. You can look at all the features, and then there's also a user guide. So in the user guide, you can have a look at all of these things. So for example, in gang scheduling, you will be able to very in depth, you can see how to define gang scheduling, how it works with preemption and so on. I can share some of these resources with you guys. I'll also there are also examples in the YuniKorn repository itself. Examples for Spark jobs, which you can also start in a cluster where you have deployed YuniKorn.
Krishna, I think we can share this web link in the chat group itself. So,
so this is the section enable. Okay, I'll just share the link itself. Okay. Yep, it's in the chat. You can also join the open source community, which is YuniKorn Slack. There's a users group there where all of these resources will be very readily made available. It's very active. All the queries can also be taken up there if you face anything in later on installing it. So yeah, this section will tell you how to enable gang scheduling for Spark jobs.
Hi, Krishna. I'll just
It will also go through hard gang scheduling and soft gang scheduling. So that will answer one of the questions which was asked by, I think, Shreyas, that what happens with preemption and gang scheduling, I think. Yeah, sorry, I interrupted someone.
Yeah, no worries. So I'll just extend the earlier example, right, regarding the Spark job to when two jobs are submitted in different queues. And let's say in the first case, the Spark job is running with one driver and 10 executors, and the second job is submitted in different queue, which can preempt the resources from the other queue. And that job requires, let's say, just one driver and then 5 executors. And let's say if all the laws of preemptions are met, and if the job or if the queue can release the resources from the other queue, or which are required just for 5 pods or 6 pods, one driver and 5 executors, it can somehow run. So does it mean that it can just get rid of 6 executor pods from the earlier queue so that the second Spark job can run? Does this happen? If yes, then does the gang scheduling law or a framework, does it mean that it gets rid of the job completely? Something like node affinity, right? When it is required during scheduling, not during execution.
Yeah, so if I can double check and confirm on this, but if a gang scheduling job is interrupted because of preemption, then the application is marked as pending.
Pending, okay. It's not necessarily purged, right?
No. There's no purging happening because these are generally submitted as deployments. And to talk more about the example of what happens, I mean, this diagram kind of shows it very clearly, where two applications are running in different queues, and with preemption, as soon as the second application comes, it preempts the other one till the capacity which is taken by that above guaranteed. And if it was a gang scheduled application, then basically it will act as if this has just come up and the gang scheduling has not yet completed. Does that make sense? Like if some of the executors were purged, it will act as if it has just come up and the scheduler is looking for all the resources. And as soon as this one runs, it will have all the resources. So it will again schedule on the new Spark executors there.
Okay, so only after the completion of App 2, the App 1 would resume from where it left off, right?
Yeah, because if App 2 has preempted App 1, that means that it has either a higher priority, first of all, and it also means that App 2 did not have its own guaranteed met while App 1 was already above guaranteed. So if preemption had happened, then those conditions must be meeting in the first place, which means that yes, the preemption of App 1 happens and then it comes up again.
Thank you.
Go ahead. Do we have any further questions? Cool. So I think we are on time. Thank you so much, Krishna, for this insightful session. That was really great. And thanks for the participation, guys. Great questions. Okay, so we have the recording also of this, which will be published at LinkedIn and Meetup.com as well.
Sure. Thank you, everyone. And for any more questions, you can contact me on LinkedIn, my email as well. I think those will be part of the community posts that are shared on Meetup. And I'm more than happy to answer more questions, discuss more, talk about corner cases. And also you can join the Upstream Slack. All of that will be part of the YuniKorn website, which I shared. So all the resources for contributing as well as for an end user will be there. So we can discuss more if required. Thank you.
Cool. Thank you so much. Have a nice day, everyone.